This is section 2.8, related rates. In this section, we will learn how to compute a rate of change of one quantity in terms of the other quantity, how two quantities or sometimes even more quantities depends on each other. Related rates are the word problems, which means we do have some steps, some procedure that we have to follow. We will read a problem carefully, as always. We will draw a diagram if possible. Having a diagram, always we have to introduce a notation. Okay? We will assign symbols to all quantities that are function of time. That means this is really important. Having a diagram again and introducing a notation, let's say we will pick some quantities. We will pick x, possibly y, z, or a, b, c, and so on. That means this is really important. We have to always remember that each quantity is a function of time. If we will differentiate, because this is related rates, not only the quantities are important, the important thing is how the quantities are changing with respect to time, which means the derivative will be involved. Now, differentiating and remembering that they are the functions of time, let's see what is the derivative. That means having x, derivative of x will be dx dt. Please remember it's not 1. Derivative of y will be dy dt. And respectively, the same for any other letter, any other label that you choose. dz dt, dA dt, derivative of b, dB dt, rate of change of c with respect to time, dc dt, and so on. That means please remember each quantity is changing with respect to time. Okay, the next point is we have to identify what is known, what is given, and what is required. Which rate is given, which rate is required. Now, having all of these quantities, x, y, z, any other, we have to try to make the relation. We have to relate them, which means we have to find an equation that is connecting both of them or more of them. Then, since we're looking for the relation between the rates of change, we will differentiate. And after the derivative, after having a relation of the rates of change, we will substitute all of the given information, all of the given quantities, and then solved whatever we were asked to do, whatever we have to solve for. We do have a few things that we have to be careful, because we can't substitute the exact value before, like in our relation in the 0.5. We always have to wait until the derivative will take place. Okay, that means let's see a few examples. I do have example 1, but I did type the solution. You can pause the video and you can look at this question. I have example number 2, which I also have typed solution. You can also look at this. I have example number 3. Actually, in example number 3, I think the triangle is missing. I can draw a triangle for you. Let's actually read the question. Two sides of the triangle are 4 and 5 in length. I mean, I can say this is 5, this is 4. And then we will draw a height, okay? And the angle between them, it's theta. Okay, that's me now. I think we will be looking at this triangle and you can follow the solution. Example number 4. Let's draw the situation and you will follow the solution. A plane flies horizontally at an altitude of 5 kilometers and passes directly over the tracking telescope on the ground. That means I'm imagining that plane is traveling, that's ground, and that's the telescope. That means we can track the plane. Plane is, of course, flying away. Okay? When the angle of the elevation is pi over 3, this angle is decreasing at the rate pi over 6 radians per minute. We do have listed this. How fast is the plane traveling at this time? That means the distance behind the plane is the speed. Okay? And that angle is the angle of elevation. That means now let's just draw one triangle which will represent the situation. That's the telescope, that's the plane, that's the angle of elevation, and this is x, the the distance that the plane passes, and how x is changing we have to actually find out. Example number 5. It's about a cube. We don't have to draw a cube. Example number 6 is about a cone. You can follow my solutions. And example number 7 is not solved. Then let's do it. An angle of elevation of the sun is decreasing at the rate 0.25 radians per hour. How fast is the shadow cast by 400 feet tall building increasing when the angle of elevation of the sun is pi over 6? Okay, that's me. Let's see what we have. We do have a building. I will draw for you. We have a ground, we have a building. Building is 400 feet tall, which probably I can use that quantity, 400. And we need a sun. That means when sun is here, that's the shadow cast, okay? And then the sun is coming down. That means when the sun is here, the shadow cast is of course longer. And when the sun is even lower, the shadow cast is even longer, okay? That's, we can see the situation. Let's draw it, just one situation, okay? I will draw a building. I will draw a shadow. Okay, that means this is okay, and this is 400, and the angle of elevation, of course, is this one, theta. And this distance is changing. That's the shadow cast, the blue, and I will label x. That means let's see what we have. We do have an angle of elevation of the sun. That means theta is changing with the rate 1/4, actually, I can say. 0.25 is a quarter, 1/4 radians per second. The rate of change of theta with respect to time is 1/4 radians per hour, not second, hour. How fast is the shadow cast of the building increasing? We're looking for dx dt, the rate of change of the quantity x with respect to time. At the moment, when the angle of elevation of the sun is pi over 6, which is 30 degrees. But please remember, that's what I would like to point out, this angle is not pi over 6. This angle is constantly changing because we know the sun is getting lower and lower, the distance x is getting longer and longer, which means the angle is getting smaller and smaller. That means this is just the moment we want the rate of change of x at that moment, which we will use this after having a relation and after differentiating. Okay, what relation I can use? I have 400, I have theta, and I have x. That means I can combine them together in probably one of the trigonometric ratio, and I will say maybe cotangent. Cotangent theta is x over 400. I could possibly use tangent, but tangent will give me x in the denominator for this ratio, and will be a little bit more complicated to get the derivative. I can solve for x, just to avoid fraction, 400 times cotangent theta. One thing, I make one small mistake. Let's read the first sentence. An angle of elevation of the sun is decreasing. And we remember, if the rate of change is decreasing, is negative. That means it's negative 1/4. Okay? And actually x, we can see the quantity x will be increasing, which means I'm really expecting a positive answer. Okay, that means this is my relation, x equals to 400 cotangent theta. Now I can differentiate. Derivative of x is dx dt, because x changes with respect to time. Copy a constant 400. Derivative of cotangent is negative cosecant square theta times derivative of theta d theta dt. Okay, now I can substitute everything. 400, or possibly I can put this negative in front, because negative is not squared. Negative 400 times cosecant, and now I can put pi over 6. And I will square the quantity, and the rate of change of theta is negative 1/4. Excellent. Negative times negative will give me positive. I can simplify 4 and 400. We will get 100. Negative and negative is positive, 100. And now cosecant is 1 over sine. 1 over sine of pi over 6 to the power of 2. Sine of 30 degrees is 1/2. Reciprocal of 1/2 is 2. Okay, that means I have 2 squared is 4. 4 times 100 is 400. That means the rate of change of x, okay, of the shadow cast of the building with respect to time is 400, and we need distance over the time. Distance is in feet, feet over hour, per hour. I can write 400 here also. Okay, that means this is my final answer. Okay, let's look at other example. Okay, let's solve the cone problem. I did solve the cone problem before, but we can solve it again. Let's see. A water tank has the shape of inverted circular cone with the base radius 2. We can see this 2. And the height 4. The height 4 is here. If water is being pumped into the tank at the rate 2 meters cubed per minute, okay, that means this is rate of change given, find the rate at which the water level is rising when the water is 3 meters deep. Okay, that's we can see the big cone with the radius 2 and the height 4, and we can also see the small cone which actually the water is creating. That's the small cone. Okay, and we're looking how this height, they asking us find the rate of change that the water level is rising. That means how this height is changing because it's getting higher and higher. Okay, I don't want to mess up my graph. That means first of all, let's see what is given. This is the volume. Given information are the rate of change of the entire volume. That means rate of change of volume with respect to time. I can possibly use the blue color because it's related to the blue cone. The rate of change of volume with respect to time is 2 meters cubed per minute. You can also note cube. Cube is giving me the volume. That's the reason that I know that. Okay, and the required information is we have to find out the rate of change of the height with respect to time. Okay? At the moment that the water, the height is 3 meters deep. We remember height is not free. We have to be really careful with this. Height is not free because we can see one more time, height is changing. Height is the water level is rising. Okay, that means height is not free. They asking us at the moment that the height is free. That's we have to find the relation between volume and the height, which probably will be just the formula for the volume of the cone, which I am providing for you. Let me copy this. The relation will be volume, it's 1/3 pi r squared h. And everything is related to the small cone, the blue cone. Okay, that means I have the rate of change of volume, I'm good. I am looking for the rate of change of the height. This is also good. That means radius is not really welcome in this formula. I have to find additional relation between height and radius. And what I see something like similar triangles. I see 2 and 4. That's the dimension of the whole cone. Okay, we can see 2 and 4. And I also see the small. I can see radius and height. The small cone, radius and height. And having these similar triangles, I can get the relation. Let's say 2/4, which is radius over height, is the same like radius over height. And I can solve this equation for radius, which will be 4 radius over 2h, which actually is 2 radius over h. No, something is wrong. Something is wrong. Radius will be 2h over 4. Okay, we have to cross multiply. Oh, hang on, I am messing up. 4r over, that means radius is actually 2h over 4, which is h over 2. Okay, that looks better. Okay, that means this is radius in terms of h. That means I will substitute this instead of r in my volume formula. 1/3 pi and h over 2 squared and another h. Okay, let's see. We do have h squared and h. This will be h cubed. We have 1/3 and 1/4, 1/12 pi. Oh, I can put pi on the top. And I can put h cubed a little bit closer. Okay, that means this relation is perfect because it's just relate volume and h. And now having this relation, let's differentiate. Derivative of the volume is dv dt, copy a constant, pi over 12, and derivative of h cubed, it's 3h squared dh dt. Okay, and now I can substitute, now instead of h, I can substitute 3. Because I have my relation, I have my derivatives, and I'm looking for the rate of change of the height, dh dt, at the moment that the h is 3. And you can probably simplify this, and I did type the final answer, but let me try again. dh dt will be equals to dv dt is 2. Let me do, okay, 2. And then I can simplify a little bit. 3, oh, that's the highlight. 3 and 12, this will be 4 pi over 4 and 3 squared dh dt. and 9 and 8, because I will multiply, let me use that part, multiply by 4, we will get 8 9 pi dh dt. And when I solve this for dh dt, I will get that value. dh dt is just 8 over 9 pi. And this is height, this is the distance, that means this will be meters per minute. Okay, that means that's how we can solve this problem. Okay, and let's solve maybe one more. I will pick another question for you. I mean, theoretically, I can pick any. Okay, let's try the multiple choice, which looks like an exam type question. Okay, the rocket travels vertically at the speed 20 kilometers per minute. The rocket is tracked through the telescope by the observer located 30 kilometers west from the launching pad. Find the rate at which the angle between the telescope at the ground and the ground is increasing when the rocket has traveled 40 kilometers. Okay, that's mean, let's see, the rocket travels vertically, that's mean we will probably have something like that. That's the rocket. Alright, that means it's starting from the ground and it travels up. I will label that distance x. And speed, which is the rate of change of distance with respect to time, it's 20 kilometers per minute. Okay, that means is the rocket is tracked by the telescope, which is located 30. That means this will be telescope and this is 30 kilometers west. Okay, actually works. Find the rate of change at which the angle between the telescope and the ground. Okay, that's we're looking for that angle. It's of course increasing because the rocket is going up. Okay, that means the angle is increasing when the rocket has traveled 40 kilometers. That's we're looking for the rate of change. This is given. This is required. The rate of change of angle with respect to time at the moment when the rocket travels 40 kilometers. That means when x is actually 40. Okay, 40 kilometers. Okay, we do have x, 30 and theta. We need the relationship. And I'm guessing again is the trigonometric ratio, because as soon as the angle is involved, I will use the trigonometric ratio. And tangent, theta, it's x over 30. X is 30 times tangent theta. And now I have to differentiate. Derivative of x is dx dt. 30. Derivative of tangent is secant square theta d theta dt, because each quantity is a function of time. Let me check if nothing is decreasing. No, this is definitely the rate of change is positive 20. Okay, now we can substitute everything. I should actually cross this one. We remember that. Since x is not really 40, is at the moment that is 40. Okay, that's we're looking for d theta dt. dx dt was 20. This is 30. Secant theta. Oh, we don't have a theta squared, and we're looking for d theta dt. That means we have additional thing. We only know that we're looking at the rate of change at the moment that this is the x is 40. This will stay 30. That means I have to figure out, okay, if this is 30, this is 40, this is probably 50. Yes, we remember, based on the Pythagorean theorem. 3, 4, 5. And we're looking for secant theta. That means secant theta at the moment that x is 40. Secant is the reciprocal of cosine. That means this will be 50 over 30, 5 over 3. Okay? That means instead of secant, I can put 5 over 3. Let's compute everything. Oh, I need a little bit of space. 20, 30, 5 over 3 squared, 25 over 9, and d theta dt. We can simplify by 10, okay? And I can also simplify 3 and 9, 1 and 3. And multiplying both sides by 3, 3 times 2 is 6, 25 d theta dt. Okay, that means d theta dt is simply 6 over 25. And the units are, because it's an angle, radians, and time was in minute. Okay, that's my final answer, which I think is this one. Okay? That we can see always the same process. Identify what is given, identify what is required, find the relationship, differentiate, and substitute all of the values.